Hi, I'm George, a technical lead here at Codesmith, as you can see on the hoodie. And today we're going to talk about recursion, one of the most complex and challenging concepts in all of programming. So today I'm hoping to break it down by digging into the fundamentals, starting with a question. Now we know in JavaScript that functions can call other functions, but what happens when a function tries to call itself? So let's actually look at some code and see what this might look like. Let's say we have a function and we'll call it recurse, okay? We won't give it any inputs. We could, but we're going to choose to leave the inputs empty. And all we're going to do is just call the function recurse. That's it. And so this right here is just a function definition. This is just stored in memory. We haven't actually executed or called this function. So if we tried to run the code, nothing would really happen. By the way, I'm using REPL.it is a fantastic online tool. You can go ahead and load this up in your browser right now. Just pick JavaScript and you can follow along using JavaScript as a vehicle to learn recursion. Now what happens if I call this function and try to execute it? Because inside of this function, it just keeps trying to call itself. It's trying to reference itself to call itself, which calls itself, and so on and so forth. So I'm going to say this is actually not going to give us a syntax error. A syntax error would mean that our code is incorrect and we have violated the laws of programming. But we're actually going to get a different kind of error. And if you think about why this kind of infinity process of calling ourselves repeatedly, that's why we're going to get this particular error. When I run this code, we get a range error. And it has a very specific error message. It says maximum call stack size exceeded. Now, if you've worked with recursion before, you know this infinite loop is a problem, and you see this error message frequently when you forget to stop your recursive calls at some point. And as you can see here in the code, we actually never stop this. This will go forever. So the computer just says, hold up, pump the brakes. We're going to stop right here because we have no more memory to keep calling this. And I want to actually jump into a diagram right now. If you have a pen and paper at home, feel free to draw this out and follow along. I'm going to show you what's happening on the call stack. So let's say that this is our call stack. Okay, it's our call stack. And the stack is just a data structure that allows us to add things and then pop things off. It's got two methods, push and pop. And so in this case, this is tracking calls, function calls. And so when we make our first call to this recurse function, this is what it's going to look like. Recurse will take up this frame. This one frame represents this one function call. And the thread of execution is going to move to inside of that function code block. And when it reaches that code block, it's going to see another call to recurse. So it's going to, in fact, add another frame to the call stack. And it's going to continue to do this forever. It's going to add another and then another and so on and so forth. And what do you think is going to happen? Even just on this visual that we have here, we're going to reach some limit of some sense. In this case, it's a physical top, but of course in a computer, it's just memory. And so you could have a few really big calls or a lot of very little calls. But either way, it's going to hit the top of the call stack, and that's when we get this error, maximum call stack size exceeded. And so how can we prevent this from happening? This isn't very useful to us to have this infinite loop. And so all we need to do is in this function block, we just need to simply have some case where this doesn't happen anymore. And in recursion land, we call that a base case. So if you've worked with recursion, you might have heard this term before. It's really important. It's saying there has to be some condition upon which we stop this infinite loop, right? A function can call itself, but there needs to be some point where either a global counter hits a certain number or we've built up our array to a certain length. Whatever the condition is, it has to eventually reach that condition so we don't exceed the call stack size. Now, I'm going to show you, just to help you visualize, just how much memory that my particular computer has. And let's see what REPL does when I create a global counter initialized to 0. And I'm just going to log that counter after incrementing it in my function. So in this case, when we hit line 9 and we call recurse for the first time, it's going to create a new frame on the call stack where we actually dive into this function's execution context. We actually increment this global counter here, right? There's no local variable called counter, but there is indeed a global one in its outer scope. And so this will become the number 1. Then when we log the counter, we should see the number 1. And when we call recurse again here on line 6, all that's going to do is just call this code block again, this code block represented by the function recurse. So we're going to increment the counter again to 2 this time, and we'll print out 2, and so on and so forth. We should see how many counters this build up before the max call stack size is exceeded. So let's try running this code and see what happens. And we run it, and we actually, of course, are going to get the same error because we haven't stopped, we have no condition upon which this recursive call will end. But this is kind of cool. We can actually see that the counter goes up here to 17,878. Whoop, trying to highlight it. Here we go. And so all this means is that this call was repeated that many times, and then the computer just said, hold on, sorry, I literally can't add one more function call to this call stack. We have exceeded all the memory that this computer has. And so now we just need to think, okay, if we have this counter that's increasing constantly, let's just throw in a condition, in this case, that can end this call. And a very easy thing that we could do is say if, for example, counter is exactly equal to the value 2, then let's go ahead and return the string done. And so the idea here is that this is our base case. We're saying when counter is 2, stop recursion. And the return statement is what is ending this particular call. It shuts down this function call, this execution context that's created. And then whatever we return is spit out to the previous call if we have returned in that previous call. So for example, in this case, I would need to return the call to recurse to actually go ahead and extract that value down from the depths of the recursive call. The way it works is that when I do reach a counter value of 2, I grab the string done, that execution context closes off, I pass done to the previous call right here on the previous call, whichever activated that call, to actually go into that execution context to reach that base case. We're going to diagram this in a second if you're not following along. Just trying to articulate it briefly before diagramming. And then finally, if I were to console.log this value right here, we would actually see printed to the console the string done. So let's run the code. Aha, so we see that the counter inside here becomes 1, and then it becomes 2, and then in the next call, that string done is returned, and it sort of bubbles back out to that top call, and that's what we're seeing printed here. I want to make a quick note in REPL that this green arrow represents the return statement or output of the final line, the final statement of code here. REPL is short for read eval print loop. And so this is just printing whatever was evaluated in console.log, but console.log function itself doesn't return anything. And so that's why we see this undefined. Just in case you were wondering what that undefined is about, it has nothing to do with our call to recurse. The console.log will always print in white on this particular tool. So let's now go to the diagram and see what this looks like. All right, so let's say that we have the call stack here on the left side. So write this down, call stack. And on the right, we're going to have the global variable environment. So here I'm going to write the word global to represent this global variable environment. And here I'm just going to put all variable assignments and operations that will occur as we go through the global scope. So here, if we run through this code line by line, the very first thing we encounter, that the computer will encounter when it's reading this code, is let counter be assigned a value of 0. And so we are going to initialize a label called counter that has a value of 0. And this is now tracked in global memory. And so next we have a function called recurse. And this is actually, I'm just going to draw a little box with some arrows for input and output. This just means that it's some block of code that is going to take in some input and spit out some output. And it might do other things, it'll have other side effects potentially inside, but in general it's just a definition. We haven't actually called this function yet until we get down to line 10, where we are actually calling the function recurse. And so now that we are calling the function recurse, I'm going to switch to a different color. Let's say right here that outside of the global variable environment, this represents our global execution context. This is which code is being executed at any given time, and this is what the call stack is tracking. This is our thread, in other words. And so let's say right here that we create this execution context. I'm going to extend it as far as I can, give us a bunch of room. All right, so we dive into this recursive call, and we see that the first line says if counter is triple equals to 2, return done. And so the computer is going to see counter, it's going to check this logic, is counter exactly equal to 2? And there is no local variable counter, which is, it will first look in the local scope. It won't see a counter. It will then go out to the global scope, see counter, and say, oh, that's 0. This isn't 2. So in fact, this will evaluate to false. And that means we do not enter our base case. We don't enter our if statement, our conditional statement here. We just continue down the line. And so next we have an increment to counter. And so when we call the increment to counter, again, there is no local variable called counter. So we look in the global scope. We actually see this variable counter, and let's assign it a value of 1. I'm going to use a color to represent the last thing that influenced it. So from the blue context, we made counter 1, this dark blue. Now I'm actually going to go ahead and get rid of this console.log here in the code. And so we can actually just track this recursive call without any side effects of printing. So next we have a return to the call recurse. So I'm going to use a different color. Let's go ahead and make this red. Now I'm going to call the function recurse. And since this is a call, oh, this was my bad. I should have, when we opened up that first execution context, I should have added a call to the call stack, because the call stack is tracking our thread, and this is where the code is right now. This is where it was. But now that we have this new call to recurse, it is going to create a new frame on the call stack, new frame, which represents its execution context. And so it's going to steal the thread. It's saying, everybody look at me. Now we're inside of my execution context. So we enter into this recurse function, and the first thing it does is say, is counter equal to 2? And it's going to look in its scope. It's not going to see the variable counter. It's going to look in its outer scope to the previous call. It's not going to see a variable called counter. And when it gets to the global scope, it will finally see there is a label called counter. It has a value of 1. And that is not equal to 2. So this is, in fact, false. That's false. And so the next line just says, well, increment counter. And so it will do the same lookup for whatever the counter is. And it's going to eventually reach the global counter and make it 2. Now I know what you're thinking, oh, we've reached the base case. But in fact, we are not at the base case just yet. The base case is only reached when that particular if statement is executed. And the next line of code is another call to the recurse function. So let's go with purple now. So if I call recurse here again, let's see. We are going to create another frame on the call stack because we have another execution context opened up, and that is where our code is currently being run. It's where it's currently being executed. And so let's go ahead. We'll now create a purple execution context. Okay. And then the very first thing that's going to happen in here is going to say is counter triple equals to 2. And in fact, this is now a true statement. It sees that global counter variable after traversing all these scopes to look for a label called counter. And it's going to immediately say, wait, this is true. This is true. And so that means that we can enter this if statement, which has a return statement, and it's not calling the recurse function again. The recursion has finally ended for this particular function. And as we know in JavaScript, when we return something out of a function, the entire call to that function is evaluated as whatever we have returned. So if I made a call to recurse, let's say, and then that call returns the string done, then that means that that call, we can think of it as being evaluated to the string done. And so let's see what that looks like. So if I just pick, let's say this green that I use for the call stack, if we are returning the string done, then that return statement, because in our recursion we have returned all of our recursive calls, this value is going to bubble up and go all the way back out to our initial call to recurse. And so this execution context, this purple one, is going to close, and it's going to evaluate to the string done. Here, this will be the string done. And then since that's a return statement, this execution context is going to close, and this call would evaluate to the string done. And then finally, let's make sure we track on our call stack as well, just like the computer would. And now finally, we would close out this execution context because it has also hit its last line of code, which is also a return statement. And so now the thread has moved all the way back out to the global execution context, and this initial call to recurse has evaluated to the string done. And so here, if we on line 9 are logging the call to recurse, then when we run that code, that's why we see that the string done is what is printed. And if this helps really quickly, I can store this value in a variable. Because this is a string, let's call it output is going to be the call to recurse. And if I print this output, we'll see that this is actually the string that was stored and evaluated, bubbled all the way back up to this recursive call. And here we see it works just as expected. So hopefully that gives you some insights into simple recursion. This is when we call our function inside of our function once. We have a challenge set up so that you can tackle that to really understand what we've been talking about here in this video and help you apply the skills so that you can actually get like an intuitive understanding. Because it's one thing to watch a video and nod along and be like, yeah, that makes sense, and that makes sense, and I recognize what this guy's talking about. But it's another thing entirely to be able to reproduce something or to be able to even teach a concept to others. And so by doing this upcoming challenge, you are proving to yourself and the world that you truly understand this material, that you can reproduce the concepts, and that you can actually apply them to real code. So even though it's fun just sitting down, maybe eating some Cheetos and watching some videos, please do go ahead and do the challenges. They're a massively important part of this learning exercise on recursion. So take a whack at the challenge, and I will see you in the solution video.